I welcome you back to Analytics Simplified, and in this video we will be talking about isotonic regression. So we already know that any machine learning model, what it is trying to do is it is trying to learn a function f which maps predictors x to target values y. In this case, isotonic regressor will try to obtain a monotonic fit for this function, which means isotonic regression is going to believe that the function which is mapping predictor to target is monotonic in nature, and it will try to find out this function given data x and y. So when we talk about isotonic regression, one thing that needs to be kept in mind is that this basically corresponds to one dimensional data. So we have data points x1 comma y1, x2 comma y2 up to xn comma yn. That means we have got n data points which are labeled, and in each case the xi belongs to r1, which means this data point is one dimensional in nature. In addition, there is another constraint on these data points. The constraint is that xi is less than xj for all I less than j, which means as we move from x1 through xn, we will be encountering larger values of xi, which means x1 will be smaller than x2, x2 will be smaller than x3, like this up to xn. So these are the two conditions on which isotonic regressor is going to obtain a fit. First of all, the predictor will be univariate, and then these predictor values are arranged in increasing order of their values. And in given this scenario, an isotonic regressor will try to find out a monotonic function f which can map predictor x to target values y. Now, basically the assumption made by this regressor is that this function is monotonic in nature rather than linear. So this is how isotonic regression is going to differ from a linear regressor. In linear regressor, what happens is we assume that the relationship between x and y is linear in nature. However, when it comes to isotonic regressor, it believes that the relation is more of monotone rather than linear. And informally, if we were to talk about this, an isotonic regressor is going to look for these estimates beta 1, beta 2 up to beta n. So beta I for each of these points xi, so that these beta I estimates not only are able to capture yi information, but are also are monotonic, which means it will try to find out these coefficients so that beta 1 is as close as y1, beta 2 is as close as y2, and beta n is as close as yn. And at the same time, beta 1 is less than beta 2 is less than beta 3, like this. And okay, so this is the primary setting of isotonic regression. And when it comes to formal equation, the loss function of isotonic regressor can be written as, I'm minimizing this function yi minus beta I, because I have to reduce the difference between yi and beta I, and this sum of square distance is being reduced, and the subject to constraint that beta 1 is less than beta 2 is less than beta n. So given this constraint, it is trying to minimize the sum of squared errors between the predictor value and the estimate it is trying to obtain. So finally, all the n values for beta I will be stored in a form of vector beta. Okay, so when we look at the backend, isotonic regressor is basically making use of a power algorithm which stands for pool adjacent violators algorithm. So I'll tell you what is the basic of this algorithm is. For more detailed description, I have put the links in the description box. So basic idea behind power algorithm is that we start from left to right. Left to right, why? Because towards the left we are having smaller values and towards the right we are having larger values, because xi values are arranged in increasing order of their values. So what we do is, first of all, for the ith coefficient we set beta I to be equal to yi, and we do this for all the values of I. And if we find out that okay, there is some beta I which is violating this monotonicity constraint, in that case this beta I is reset. So instead of assigning yi to beta I, what we will be doing is we will be replacing beta I and beta I minus 1 by the average of these two values. So in this way it is ensured that for whatever beta I we are having, those beta I values to actually conform to this monotone constraint. This monotone constraint is taken care of after this substitution. Now when it comes to applicability of this particular algorithm, this is very much applicable and it is practical because it is linear in time and space. So when we talk about the space complexity, we say that the power algorithm is linear in with respect to time and also space, and that is why it is one of the good fits or one of the better choices to make in order to solve a isotonic regression problem. So now what we will be doing is we will be looking at the basic implementation of isotonic regression on a sample data set. So naturally I'm using Python for the implementation of this particular regressor, and the environment I'm using is Google Colab, so that you are able to get a glimpse of whatever is happening in the real time. Moreover, for your for your convenience, I have added the Python codes as well as the base papers to Power algorithm also, so that you can have a look at those resources in detail. So first of all, what I will be doing is, because I have to work with NumPy matrices, so I will be importing NumPy library, and then I'm setting print options as precision equal to 2. np.print set option basically sets some printing options when we are using numpy arrays, and in this case what I have chosen the precision to be equal to 2. That means whenever I will be printing any array, the values will be printed up to the precision of 2 decimal digits. Now in this case, because it is a toy problem, so what we will be doing is we will be simulating a function which is y is equal to log of 1 plus x plus epsilon. Okay, and this function will be simulated using, or this function will be captured using isotonic regression. So in this function I can see the predictor is value x and the target value is log of 1 plus x plus epsilon. Epsilon is a random noise that has been generated to figure out how good the estimates are. Okay, so in this case we will be developing an isotonic regressor which will be able to capture this mapping. So first of all, what we have to do is we have to create some data points. So I have stored the number of data points that I will be generating in the variable called num data points. So num data points is a variable which is storing 100. That means I will be generating 100 data points. Okay, so in this case I have used numpy.arrange function and to generate these data points. So by using this numpy.arrange function, I will be able to generate 100 data points, and finally what I will be doing is I will also be obtaining the y values for each of these xi's. So how do I obtain this? I run a random command, okay, of the same size as num data points, so that this epsilon I can generate, and in addition I will be having some constant multiplied by np.log of 1 plus these values. So whatever these values were there, I have simply put it into the log function, and as a result I will be able to obtain this function. Okay, so this is how we are able to create this data set. We now have got the predictor values, and we also have got the target values. In the next step, what we will be doing is we will be printing these values. So first of all, I am printing the predictor values which are stored in a variable x, and finally I am printing the target values which are stored in a variable y. In addition to getting the values of these predictor and target variables, I am also printing the shape of these variables using dot shape function. Okay, so when I run this command, wait, I'll have to run from the starting. Okay, so here I have created the data set, and now I'm printing the shapes and the values. So what I can see, this is the predictor that I have obtained. So you can see that the values of xi are increasing with as I increases. So this monotonicity constraint which I have put with this particular regression demands is already met, that xi is less than xj for all values of I less than j. So you can see that you are having the predictor values in increasing order of their values. In addition to these predictor values, we have also got the target values from the function log 1 plus x plus epsilon, where x is the predictor value and epsilon is the random noise that we have added, okay, to simulate this phenomena. So once we have printed these values, the values for the predictor and target values, let us also try to explore the values for these shapes. So when we talk about the predictor shape of the predictor, it is 100, 1, which means there are 100 samples and the dimension of each sample is 1. Why the dimension of each sample is 1? Because isotonic regressor demands that the predictor be unidimensional, that is xi should belong to R1. That is why the shape in this case you are getting is 100, 1. Okay, likewise for the target values also you are getting the same shape, because target value is also one dimensional, and because there are 100 samples in the predictor matrix, so there are 100 values on the target vector also. Okay, now that we have obtained the data set, we have created the data set, we have printed what the data set looks like in terms of the values and the shapes. Let us also try to plot this data set for a more visual understanding. So what we have done is I have used matplotlib.pyplot in order to plot x comma y. So I will be plotting y against x. So y is the target values and x is the predictor values. So when I print this particular graph, I get something of this sort. So on the x-axis I'm having the predictor values. Now you remember the predictor values were starting from 0 and they were going up to 100 because we had chosen 100 data points and I had used np arrange function, which means the values will be in increasing order. Okay, so on the x-axis I'm having predictor values in increasing order of their values, and on the y-axis I'm having the corresponding target values. Now by looking at this particular graph, you come to know that there is not much concrete about this relationship. So that is what we are going to do. In the next step, we are going to build a isotonic regression. So isotonic regression is available in the sklearn.isotonic package. The name of the function is isotonic regression. Okay, so what I will be doing is, first of all, I will be importing this particular function and then I will be creating my isotonic regression classifier. By calling, I will simply be calling this function. Right now I have not set any hyperparameters. In the next couple of videos, when I will be discussing about the hyperparameters, I will also be explaining how the different hyperparameters in this isotonic regression are going to affect the performance. But as of now, it is a simplistic model that I am creating, so I have not put any hyperparameters. So whatever hyperparameters are there, sklearn is working with their default values. Okay, so in this line what I have done is I have created a isotonic linear regression classifier, and in the next step what I have done is I have simply fit this classifier on x comma y. X is the predictor and y is the target values. So I have fit this classifier, which is same as fitting the classifier on this data set. So it will take some time. So okay, it's done. Now what I will be doing is, now you remember I told you that initially we are not taking any specific values for the hyperparameters. In other words, I am working with the default values. So let us try to print what those hyperparameters say. So how to print them? I can use the getParam function, this getParam function, to obtain the hyperparameters for this linear regression classifier. So for this isotonic regression classifier. So these are a bunch of different hyperparameters that this linear regression is assigned or initialized with. Okay, so I will not go into the details much because we will be discussing them at length. So just for your convenience, the first hyperparameter basically requires what is the state. So state is increasing, which means the values of xi is increasing, is continuously increasing. In this setting I have chosen a case when the values are increasing, right? The reverse is also possible, but because it is a first model, so I have taken the basic setting that xi values are increasing. So that is why I have to put this here also. The hyperparameter value is set as increasing, means true. Okay, it's a boolean parameter, so I have set this parameter to be equal to true. And then I have another hyperparameter by the name out of bounds. So out of bounds hyperparameter basically tells you what to do with values which are out of the range. So in this case NaN is selected, which means any value or any test input which is having some very large values or which is having values which are not within the bounds, those values will be replaced by NaN. So this regressor will internally replace those values, out of bound values, with NaN values. And in addition to this, I have also set Ymax and Ymin values, because eventually isotonic regression is going to come up with the predictions for each of these xi's. So in this case, what we can do is, by using these hyperparameters, I can set the maximum and the minimum value that this linear regression this isotonic regression classifier should report. Okay, so we will talk more about these hyperparameters in our subsequent videos, but for the cases of completeness and simplicity, I have chosen to explain the basics of these hyperparameters. Okay, and then what I will be doing is I will also be trying to print the arguments of this regression. So in this case, what those arguments are: the maximum value of x and the minimum value of x. They can be obtained by using the arguments xmax underscore and xmin underscore. So what these values are? These values are basically the minimum and the maximum values of the predictor. So we already know that in this case the predictor is having the minimum value of 0 and the maximum value of 99. So the same values are being printed here. So minimum value is 0.0 and the maximum value is 99.0, just because there were 100 points in this data set. So they are starting from 0 and they are going up to 99. Now that we have trained a classifier on the feature matrix. Now we will be trying to make predictions. So as of now I have chosen the same feature matrix to be the test input, and to make predictions I will be using dot predict function. To this function I will be passing the feature matrix X, which is having my univariate values. So the predictions which are made by this classifier, they are being stored in a variable called isotonic regression predictions. And in the next step what I will be doing is I will be simply printing these prediction values. So let's do this. So these are the values which my isotonic regression has predicted for each of these xi's. Okay, so if I were to find out the shape of this particular prediction, it will again be 100, because there are 100 points in the matrix X, and corresponding to those 100 points in matrix X I will be getting these 100 different predictions. Okay, and in finally what we will be doing is we will be comparing the ground truth values and the predictions that are made by the classifier. So what I will be doing is I will be using an np.columnStack function. So np.columnStack function, what this function does is it places two columns next to each other. Okay, so in this case the first column that will be there will be containing the ground truth values, and in the next column we will be having the predictions made by the isotonic regressor. So you can see that this first column is having the values, the target values, which were already given to us when we created the data set. Okay, and in the next column we are having the predictions made by this isotonic regressor. Okay, so what I have done is, for the sake of visually understanding what the numerical values are, I have put these columns next to each other to find out how the isotonic regressor is making the predictions. Now in the next step what I will be doing is, you remember in the previous case what I did was, when I created the data set I plotted the target values against predictor values. Now what I will be doing is I will be plotting the predictions, so there's a mistake. So predictions. Now I will be plotting the predictions made by the classifier against the predictor values. Okay, so in the previous case it was ground truth versus predictor values. In this case it is predictions versus ground truth. So when I plot this particular graph, an interesting pattern is coming. So what the pattern is? The pattern is that the blue lines that we are having, they correspond to the actual ground truth values. As you can see in the legend, the blue line basically corresponds to the actual values of y, and the orange line, it basically corresponds to the predictions that my model has made on these points. So two or things are there which are worth noting. First of all, what we can observe from this particular graph is that unlike the ground truth values, the predictions made by this model, as you can see using orange color, the predictions made by this model are now monotone. They are non-decreasing. They, for given values of xi, they are either constant or they are increasing with respect to xi values. Okay, so this is what we meant when we said that isotonic regressor assumes that the function is monotone and it tries to fit a monotone function. So as you can see in this case, this regressor has fit a monotone function which is not decreasing. Okay, and in most of the applications of isotonic regressor you will find these kind of patterns. We also say that isotonic regressor in a way is fitting fitting piecewise step function. So you can see this is a step function, this is again a step function, this is again a step function. Okay, so in other words what we can say is that for given values of xi, isotonic regressor comes up with piecewise step functions, and it tries to capture the mapping from x to y using these piecewise step functions. Okay, so I believe that you have now understood what the function of this isotonic regression is all about. So first of all, it is trying to predict yi values for each of these xi's in such a way that not only the squared error is minimum, but also the values predicted are monotone, which means, as you can see in this case, the idea was to get these beta I values so that beta 1 is less than beta 2, like this. Okay, so the monotone predictions are obtained using isotonic regression. Now that we have obtained the predictions and we have compared what the shape of these predictions is going to look like and in what way isotonic regression is able to capture a monotone function, we will now also try to capture how well the fit was. Okay, so in order to find out the goodness of fit, we will be using R square coefficient of determination for the predictions. the formula is given as follows. And in case you want more detailed description about this R squared coefficient, I have shared a link that I have created. Okay, so you can go to that particular YouTube link, and in that particular link I have discussed in detail the significance of R2 square coefficient. In this case I am using R2 square coefficient, so this particular coefficient is available in this score function. So what I will be doing is I will be using the linear regression, the isotonic regression classifier, and using this classifier I will be calling the score function, and to this score function I will be passing the x and y values. So what this function is going to do internally is, using these x values, it will be generating this predict array, and using this y true, this y is actually the ground truth values. Okay, so by using x it will get the y predict values, and then it will use the y predict and y true values in this particular equation to give you the R2 score. Okay, so in the next step what I have done is, I have whatever R2 score I have obtained, I have rounded it to 3 decimal places, and I have simply printed the value. So in this case you can find out that the fit is not so good because I have taken the random values. So but then when you are building your own applications, this R2 score coefficient could be a good way to find out the goodness of it for your model. Okay, now that we have discussed what isotonic regression is all about, how it is able to capture a monotone function, let us also try to understand the applications or the scenarios in which we should be going for isotonic regression. So primarily, by its very definition, isotonic regression should be used only when some monotonic fit is enforced on the data. Okay, when we know for sure that the target values are bound to increase only. For example, when we talk about number of sales in a company with respect to days, or total number of sales that the total, if we talk about total number of sales that a company has achieved over a period of 100 days, for example. Okay, so in that case we know that the total number of sales will be a non-decreasing function, either it will remain constant or it will not decrease. So that is one application where we know for sure that the y values will be monotone in nature. So in those kind of applications we can go for isotonic regression. Okay, and in some cases what can happen is, by using this isotonic regression, the values obtained by this isotonic regression could be used as labels to train further classifiers. So these are the two cases in which we may go for isotonic regression. So with this we come to the end of this particular tutorial. In case you have learned something new, feel free to share this among your friends.